Good morning. Welcome back to another sunny Berkeley summer day in mid-July, in the beginning of July. I was like, the weekend was so nice, and so I had my shorts out, I had my t-shirt out, enjoying my July 4th weekend, and I woke up this morning and I was freezing. And then I was like, yes, this is a Berkeley that I remember. Okay, so we have some announcements. Homework 2 is due tomorrow. We've got a lot of questions on whether we mark points off if the graph does not look exactly like the plots that we have in the homework. This applies to both homework 2 and 3. If your graph looks slightly different, we won't mark you off. So like a lot of times your aspect ratio of the plot won't be exactly the same, like the width and height of the plot won't be exactly the same. You may have different colors, for example. You may have different like X or Y limits. And so we won't mark you off if those little details in your plot do not match our plot exactly. But we will mark you off if there are some clear differences in the data that you're plotting. So for example, if in our plots there are 2 colors and you've only plotted 1 color, that would be to us like a major difference. If the trend in our plot is like an upwards trend and in your plot it's like a flat line or a downwards trend, that would also be a major difference. So basically, don't worry too much about the aesthetic of your plot as long as the overall pattern is still there. If the overall pattern is there, we won't take any points off, even though like your limits or your colors might be slightly different than ours. Okay, we got homework 3, which is due Friday, and we got a midterm next Tuesday, which will take place in class. It'll be from 9:30 to 11, but we'll start at 9:40 sharp. So if you get here after 9:40, you'll have less time to take the midterm. So I do recommend you get here at 9:30. I may start the midterm early to reward those who come early, so do come early. Okay, so we will allow a single handwritten 2-sided cheat sheet. The only reason why we say it's handwritten is so that people, because a lot of times when we say like it's not handwritten, people will just take the slides and make them real small. And I think I put the wrong day here. Yes, it's not tomorrow. It is next Tuesday. What's next Tuesday? It is the 16th. I'm sorry. Sorry for scaring you. Here we go. Is that why you guys are raising your hands? Okay, yes. No, the midterm is not tomorrow. It's next Tuesday. And the material will cover weeks 1 through 3 of class. So it'll cover everything that we talked about in class. Discussion and lab, all of that is and homeworks and assignments, like all of that is fair game up to and including this week. Okay, so from the beginning of class till Thursday of next week is fair game for the midterm. Thursday of this week is fair game for the midterm. On Monday next week, we're going to be having a midterm review in place of a normal lecture time. So if you want to do some practice problems or go through some review, we're going to reserve Monday's lecture for that. And for the midterm next Tuesday, we will be giving everyone attendance for showing up to the midterm, as long as you're here for the midterm. Yes, Daniel? You don't have to come to lecture on Monday, but we will be taking attendance. Yeah. Okay. Any questions on that? Okay, so we do plan to send out an email on Piazza with the full details, but I just wanted to give you a heads up so you guys can be aware that we've got assignments this week and a midterm next week, so we kind of have to stay on top of things. Okay, if you are a DSP student, I have some good news. I actually got put into the system today, and so I'm getting like a flood of emails with all your letters. And we plan to email you today with details about taking the exam if you have some accommodations for exam time. Okay, small group tutoring this week. So if you want some smaller group help for the concepts in this class, you can go ahead and sign up on that form. And our small group tutors, I think, will be updating some times later today. All right, let's talk about databases. So a database is not so different from what we've seen so far in this class. Basically, a database gives you a principled way to access lots of data. And so in this class so far, what we've done is we've had all our data in CSV files. And in the real world, instead of working with a bunch of CSV files, people work with databases. And one primary reason that people work with databases is because in a CSV file, if you want to update that file, if you want to update your data and send it around to other people, you have to kind of like edit that file manually. You have to email it to other people. You may not be sure whether their copies are the right copies. And essentially, databases give you a lot of useful features when it comes to running products or running companies or just collaborating in general with more than one person. They also allow you to work with larger data sets. So we're going to be talking about this later on in this lecture, but more or less, like a database will give you maybe access to 10 to 100 times the amount of data you can work with in Pandas or Python alone. And so databases essentially give you scale, they give you consistency, and they also give you some collaboration features that are not possible with just normal file systems. And because of that, they're just used everywhere. So if you work at pretty much any company that uses technology in the world, they'll be using a database somewhere. And in this class, we're going to be talking about one particular database type, which are SQL-based databases. And we're going to be talking about one specific database called SQLite. Okay, so in the database world, they have different vocabulary that they use to describe some data sets. In this class, we're going to be talking about relational databases, which are essentially databases that hold tabular data or data in table format. There are other types of databases out there. So for example, you may have heard of a NoSQL database. Those types of databases typically store like a hierarchical data set. I know MongoDB is an example of that. And in this class, we're going to be foregoing those NoSQL databases in favor of the SQL ones because they have more history and they're also mapped more closely with Pandas, and they're generally speaking like more broadly used in the real world. Okay, so in the database world, a relation is a table with rows and named columns. Every row in a relation is called a record or a tuple. Every column is called an attribute or field and has a name or a data type. In a database, like in Pandas, every column has some computational data type, like an integer or a string or a float. But conceptually, these data types describe some like domain of interest to us. So for example, if you have a column representing ages, you may want to enforce that that column has to be 0 or greater than 0. You shouldn't have negative ages. And in a database, you can kind of enforce those constraints at the database level. Okay. Now, if you take a databases class, they'll talk about like relational algebra, and like mathematically speaking, a relation is like an unordered set of tuples, and everything in a tuple is unordered. But in practice, it's much more useful to have everything be ordered. And so in SQL and in Pandas, the columns and the rows of a relation or a table are ordered. Okay, so one difference between a relation and a data frame is that in a data frame, every row also has a label. In Pandas, every data frame has an index, and that index gives you labels for each row. Whereas in databases like SQL or other relational databases, we don't have names for rows. Okay, so we only have names for columns. Okay. So Pandas data frames are more flexible than relational databases because you can do, you just have more flexibility in terms of the method you can do. For example, you can take the transpose of a data frame that only contains numeric data, and that sort of makes sense if you look at a data frame as like a matrix of numbers. But in SQL or other relational databases, taking a transpose of data doesn't really make sense. And so basically, types of relational databases are SQL, MySQL, or PostgreSQL, and those databases contain relations, and those relations are designed to allow some specific relational operators, including grouping, sorting, selecting, and joining, which we're going to be talking about soon. But your takeaway from this is that if you work with SQL, you have a restricted subset of methods you can do or data manipulation like operations you can do. But the trade-off there is that although you have less flexibility, you have a lot more scalability. So you can work with larger data. Okay. All right, so schemas. In a database, every relation has a schema, which essentially is kind of a description of what the table contains. Okay, so on the right here, you'll see here an example schema of a data set we're going to be using in a few minutes, where I have two relations. One relation is called users and one relation is called orders. The users relation has an ID column and a name column. And you can see that in the schema description, the ID column is an integer and also the primary key of that particular relation. So for example, if you designate a column as a primary key of a relation, SQL will not allow you to have duplicate entries in that ID column, unless you have like the same name for that tuple. But generally speaking, like if you designate a column as a primary key, SQL will want that column to be unique. Okay. The schema determines the granularity, the primary foreign keys of a data set, and the representation, the computational data types that we'll use for each column. All right. All of this should be somewhat familiar to you because if you've taken 61A, we've taught SQL in 61A. Okay, so I won't actually be going over the bare basics of SQL in today's lecture. I'm going to assume that you've taken 61A and that you have some memory of what you've learned in 61A. If you don't remember the stuff in 61A, or you haven't taken 61A, you can see that page in the 61A textbook, which goes over the basics of SQL. But I will be explaining more or less like the code that we'll be going through today, so that if you need to jog your memory, you can hopefully remember what's going on. Okay. For example, this query should make sense to you. So in this query, what we're doing is we're joining two tables, cities and temps, where the name of the city is equal to the temp of the city. Sorry, yes. And then we're selecting three columns out of that joined data set. Okay. This query should feel familiar. So we've covered grouping and having before in our introduction to SQL in 61A. But in case that doesn't look familiar, I put here a pandas equivalent. So using group by and having in SQL is essentially doing a group by and a filter in pandas. Okay, so a lot of the operations in pandas perform the same types of data manipulation as the operators in SQL. And the reason for that is because they're both based off this underlying idea of relational algebra, which describes some useful operations you can do for tabular or relational data. Okay. Talk about joins. So we've talked about joins briefly before when we used pd.merge, but we didn't talk about the types of joins you can perform. And I wanted to discuss with you several types of joins. Okay, so a cross join takes all the tuples of one table and joins them together with all the tuples of the other table. Okay, so for example, I have here two relations, S and T. Each of those relations has two columns or attributes. Okay, and what I've done in the SQL query in the bottom left corner is say select star from S comma T, which tells SQL to do a cross join between the relations S and T. So you'll see here that the first row of S appears with every single row of T. The second row of S appears with every row of T, so on and so forth. So if there are 4 rows in S and 4 rows in T, the resulting join table will have 16 rows, one for every possible pairing of rows in S and T. Okay, so you can see here, for example, that we have the first row of T joined with every row of S. This block here has a second row of T joined with every row in S. Third row of T joined with every row in S. Okay, so we have here what's called a cross join, which doesn't do anything besides just take all of the rows and try to just mash them together, even if the rows don't really make sense. So for example, if you replace the U column with emails and the V column with emails, you're going to get rows where the email doesn't match. Okay, so that's not typically something that we'll do in real life, but what we can do is use the cross join to construct what's called an inner join, where only matching rows will appear in the results. So for example, in an inner join, what we'll do is SQL will look at if we join S and T on the U and the V column, this is equivalent to saying pd.merge. We have pd.merge S comma T on the U or V column, right? So we'll do left on equals U, right on equals V if we're using pandas. And in SQL, what we'll do instead is write select from S join T on s.u equals t.v. And this syntax here says, do a cross join, but only keep the rows where the u column of s matches the v column of t. And you'll see here that the resulting table has 5 rows. Okay, so if the u column and the v column have duplicate entries, so for example, here we have x and x and x and x here, then what we'll do is a cross join between these rows, right? Because the original table was 16. Okay, so let me go back to the cross join. Doing an inner join is the same as doing a cross join, but we'll only keep the rows where the u and v columns are the same, which means that the first row we'll take out, the second row we'll keep, the third row we'll keep, the fourth row we'll take out this row, keep these 2 rows, so on and so forth. Okay, so the inner join here, the result of this table is we'll get matching pairs of rows in these 2 columns. So every entry that appears in this final table has the same value in both the u and the v columns, and the resulting table has 4 columns. 1 column for every row in the original 2 relations. One important aspect for the inner join is that the rows that don't get matched will get dropped. Okay, so you'll see here that the first row doesn't have any matching v value. There's no value in the v column that has w, and so this row just gets dropped silently. Similarly, the rows that don't match in the t relation also get dropped. Okay, so this is similar to what happens in pandas, because in pandas the default join is an inner join. So if you look in the pandas documentation for the merge method, you'll see that I believe there's an argument called method, and that method, the default value is inner, and you can specify different types of joins that you want pandas to do, but you should know that the default is inner because it will silently drop rows that don't match, which is a great way to just lose data and make your sample a non-random sample, even if it was originally a random sample. Yes, Danny?
Are all 3 of those lines both the same?
Yep, so all 3 lines of SQL that I've written here do the same thing.
So then why use inner join if this is join on the
Yeah, so basically you write inner join to be explicit, but then since inner joins were so common, it's like the most common type of join, SQL, the implementers of SQLite just said, okay, if we just say join, we're going to assume that you want an inner join because that's the most common join. Yeah, so all these 3 are shortcuts for the same thing. I personally prefer the top one just because it's the most explicit. Yeah, Jesse?
So the 2x and 3x appears twice, but 4y appears once. Why?
That's right. So there are 4 rows that contain x, but only 1 row that contains y in the resulting relation. And that happens because if you have matching values in u and v, but those values appear multiple times, then you're essentially doing a cross join between all the matching values here. So like this row is paired with both a and b. So this row labeled 2 is paired with both rows with a and b here in this column. And this row with 3 in the m column is paired with both rows a and b in the t relation. Okay, so that's why you have you have all the possible combinations of x values here. But since there's only 1 y value in the s and the t table, you only have 1 row in the result. If there were 2 rows with the y value in the t relation, then you would have 2 rows here for the inner join. That's a good question. Okay. Sometimes we don't want to drop the rows that don't match. And what we can do is do what's called a left outer join. In a left outer join, if a row in the first table doesn't have a match in the second table, it will still appear in the final results, but the columns of the other relation will be null. Okay, so the only difference between doing a left join here and doing an inner join from the previous slide is that we have this row up here, which contains 1 and w, but since there are no matching values in the t relation, it'll have null and null here. Okay. So this is useful for when, for example, you know that you don't want to drop the rows from the left table, but you're okay with dropping rows from the right table, which appears more often than you suspect. For example, if the left table contains users or students in the class, and the right table contains assignments, for example, assignments that get turned in, oftentimes in a class, we'll have people that submit assignments but then drop the class later. And what we want to do is when we want to compute the actual grades, we'll take all the students that are currently in the class and make sure that they stay in our roster. But we'll drop the assignments that don't have any matching students because those students may have dropped the class. So the left join actually appears more often than you suspect, even though it's like this weird asymmetric thing. There's a join called a right outer join, which is the exact same thing as a left outer join, except that it'll keep all the rows from the right table and drop the rows from the left table. Okay. In SQLite, there is no keyword for right join. So in SQLite, we're going to use SQLite only allows inner joins and left joins. But to do a right join in SQL, what you can do is reverse the S and the T here. So in SQLite, if you switch the S and the T, you're going to be doing essentially a right join on S and T. Yeah. Matt, did you have a question? Okay. Okay. There's one more type of join called a full outer join or just an outer join. And in a full outer join or an outer join, you'll keep all the rows in both tables regardless of whether they have a match. Okay. In practice, though, surprisingly, you'll mostly use an inner join and a left outer join. And because of that, SQLite only has those two options. So if you want to do a right join or a full outer join in SQLite, which is a database that we're going to be using in a minute, you're only restricted to inner joins and left joins, and you'll have to construct the right joins and the outer joins yourself. Okay, let's go through a demo. All right, so what I have here are two relations, users and orders. Oh my gosh. I think I need to restart my kernel. All right, let's try this now. Okay, done. All right. And so what I've done here is I wrote a little function that will print out, let me zoom in. Zoom in. This function takes in a SQL query as a string and prints out the result of that query. So what I have here is I have all the tuples in the users table and all the tuples in the orders table. And you can see here that we have 4 users and we have 4 orders. Okay. To write some SQL queries, what I typically do is I'll make a string called query. I'll make it a multi-line string in Python, which means I'll write triple quotes. And then I can write whatever SQL I want within those triple quotes. So for example, if I want to select all the users where the ID is greater than equal to 3, then I can run that by calling print SQL with my query. Okay, so when I run that query, I will only keep the tuples where the ID column is greater than or equal to 3, which means I'll keep Leo and Steph. Okay, so that's a simple query. I'm going to show you right now the cross join between the users table and the orders table. So you can see here that the data in these two tables seem related to each other. We have here orders and we have here users, and we see some matching values between the users name column and the orders name column. So I think, yes, users has a name column, orders has a name column, and so you can see here that there's a matching tuple for Sam, which looks like I spent some money on some tea. It looks like Manana spent some money on a latte. And so we can join those two tables together. We can start with the cross join. All right, so I'll just keep it in this cell. Okay. To do a cross join, we can just do users comma orders. And now we see every possible row in users paired with every possible row in orders. Okay. And to make this more meaningful, we want to do an inner join on the name column of both tables. Right? So you only want to keep the tuples where the name column is the same. And so we can write users join orders on users on name equals orders dot name. Okay, so we can see here that we only keep 3 rows, and every row is paired with the item that the person ordered. Okay. As I mentioned before, I can also write an inner join like this, so I can write it as though I was doing a cross join, but add a where clause. So these two queries will do the same thing. I can reverse this just to show you the original query. But again, I typically prefer to say join. Okay. I can do a left join. If I have a left join, what will happen is it looks like Steph here did not make any orders, but if I do a left join, Steph will still appear in my final relation. So if I do a left join, we see here that we have the same 3 rows plus a row for Steph, and in place of values from the other column, in place of the values from the orders relation, we have null values or none values in Python. All right. I'm going to show you how to do a full outer join. A full outer join is not super fun to implement. I'll just show you what the syntax is so you can see what it looks like. All right. So to do a full outer join, essentially what I'm to do is do a left join from users to orders, and then another left join from orders to users, and then union those 2 tables together to get all the possible combinations of rows from both tables. Okay, so take this query, duplicate it. I'm going to do orders, left join users, and I have to union these 2 tables together. A union in SQL is essentially saying stack the 2 tables on top of each other and then remove duplicates. Okay. And let's see. It didn't work because I need to specify the columns. Okay, so let's do users.id, users.name, orders.item, orders.price, and let me do that here as well. Okay, so we see here now that water didn't have no one bought water, and Steph didn't buy anything. So this is a full outer join. It's not super fun to do in SQL, and I'll leave it as an exercise to you as to figure out why I need to specify the columns here instead of just doing a star like I was doing before. Okay. Okay, let's see here. Doing pretty good on time, so let's take a short break. And I'm going to open up the attendance form right after I log in to Berkeley. All right, I'm logged in. And come on now, resume collecting responses. All right, go ahead and fill out attendance, and we'll come back at 10:14. All right, it's 10:14. Let's come back together. Before I move on, I did want to talk to you about the difference between the different types of SQL databases. So I briefly mentioned that common SQL databases are SQLite. Okay, there's MySQL and there's PostgreSQL, and there are probably many other types. There's Oracle database, which I believe uses a variant of SQL. And you may ask the question, like, what's the difference between those different databases if they all use SQL as a programming language to query data? And the main difference between the SQL databases is their additions to the SQL syntax. So for example, I believe in Postgres, they actually have a keyword for outer join or right join, whereas SQLite does not have that keyword. SQLite is special in that it was designed for a very lightweight usage, hence the name. And so it doesn't contain support in particular for working on the same database at the same time. Okay, so in Postgres and in MySQL, or more large-scale database systems, what you can do is have multiple people reading and writing to the database at the same time. So for example, you might have a web server that's getting requests. So when you do a Google search, Google records down what the search was. So you have one service that's recording some data, and you'll have other services that are reading out that same data as it's coming in. So for example, if I'm a data analyst at Google and I want to do some analysis on Google searches as they come in, then I can read that database at the same time that the web server is writing into the database. Okay, so that's the sort of thing that you'll need a larger scale database engine to do, such as MySQL or PostgreSQL. SQLite doesn't contain that functionality, but the pro is that SQLite is really easy to set up because Python comes with the SQLite engine built into it. As you saw, I was using a built-in package or a built-in module in Python to read SQLite. Most programming languages have a built-in module to read SQLite databases, and because of that, it's just very convenient to use. And it works really well when you only have one data set that can fit on a single machine, and you're the only one reading and writing to it, or you only have one person reading and writing to that database at any one point in time. Okay, and one pro of using SQLite over, say, a plain CSV file is that SQLite has what's called, in a database world, ACID properties. So ACID stands for atomicity, consistency, I think idempotency, and I forget what the D stands for. But basically, the takeaway here is that if you're writing to a CSV file and your computer crashes in the middle of it, you can screw up that file and never be able to open it again. In SQLite, if you're writing to your database and your computer crashes, SQLite will do the smart thing and make sure your database is still good to go. So next time when you open it, things will still be okay. Okay, so it protects you against those system crashes, and it also allows you to read in larger data. And it's convenient because it stores all the data in a single file on the file system. And so I'll show you what that looks like in 1 second. But the takeaway here is that if you're working with data that can fit onto one computer, and you only need one person to read and write from that data at any one point in time, then SQLite should probably be the database of choice. If you need something more large scale, or that can handle concurrent users reading and writing to that data at the same time, then you'll need something more heavy duty like MySQL or Postgres, and that will take you a lot of time to set up because those things are complicated. Okay. All right. I want to talk to you about a little extra SQL syntax that comes in handy when it comes to practical data manipulation. One of them is the in operator. So in Pandas, we have something .isin, and in SQL, we have the in keyword, which essentially does the same thing. So in this SQL query, I'm checking to see whether the month is any one of those three values, January, March, or May. There is also the like operator, which tests whether the string matches a pattern. It's not a regex, but it behaves kind of like a regex. So in SQL, what we'll do is the wildcard character is the % sign. So in this case, what we're looking for is all the times essentially where the minute is 0, right? So we have here the % sign says you can have any number of characters come before and the percent at the end of the string, so you can have any number of characters come afterward. And so this specific query will check whether the time contains the substring :00, which could indicate, for example, like times that occur on the hour, or perhaps times that occur on the minute. Okay. As I mentioned before, data sets that are too large to fit in a pandas data frame can often fit in a local database like SQLite. And the basic reason for that is that databases are limited by your disk size on the computer, while Python is limited by your memory size. Okay, so if you go into your computer settings, or when you're buying your computer, you'll often see like different options for memory as well as disk or hard disk storage, or HDD as it's sometimes called. And the difference between those two is that on your computer, the disk is usually pretty big, but it's very slow. Okay, so you can have like 1 terabyte of disk space, which is relatively common nowadays, which is much larger than the few gigabytes of RAM that you'll usually have in a computer. So in a computer, when you're buying a computer, you'll see RAM, which is short for memory, or random access memory. You'll also see like disk space or disk storage, which is short for disk size. Okay, and usually the disk size is much larger than the memory size. And in Python in particular, when you're running a program, that program will always run in your memory. It will always make use of your computer's memory, not particularly your disk. Okay, so when I'm running a program in Python, it allocates memory to run that program. And because of that, you're limited in the size of data you can work with in Python, because you're limited by your memory size. Databases like SQLite and other other databases like SQLite are limited by the disk size instead. Okay, so basically that means that if I have a 4 gigabyte RAM, but I have like a 1 terabyte disk size, then using SQLite will let me work essentially with like a terabyte of data, whereas working in Python will let me work with essentially a gigabyte of data. Okay, so usually the order of magnitude is like between 10 to 1,000 times larger for these SQL databases, which is one of the reasons why we use them. Okay, and so a common pattern that you'll see, and that I'll demonstrate right now, is that we'll take a large data set and realize that it's too big to read into a pandas data frame. So what we'll do is we'll stick that data into a SQLite database, and then do some manipulation and slicing in SQL, so that we can get a smaller data frame to work with in pandas. Okay. For today's demo, I went to the IMDb website. And the IMDb website, let me just show you what that looks like here. The IMDb website is like this database of movies, and it contains movies it contains data on movies since pretty much the beginning of movies. And you'll see here that they freely provide their data for us to use. So we have here one database for the titles of the movies, one database for the crews of the movies, like episodes of TV shows even, the ratings of movies, so on and so forth. Okay, so what I've done here is take the movie titles and the names of actors and actresses in these movies. This function here is the same fetch and cache function that we've been using in other assignments in the class. So I'm going to download that data. In this case, I already have the data saved, so it runs pretty fast. I'm going to unzip it, and you can see here that when I run ls-lh on the command line, these data sets are pretty big. Okay, so I have here the names data set when it's unzipped is like half a gig. The titles data set when it's unzipped is 400 megs, which is roughly half a gig. So these two data sets combined are about 1 gigabyte of data. And since I have like Chrome running on my computer and all these other windows open on my computer, if I want to read these tables into pandas, I'm going to have a bad time. It's just going to crash my kernel. And if I was on DataHub, it would crash my kernel. I'm running this on my own computer, and what I'll do to my computer is just make everything run really, really slowly because I'm going to run out of memory. Okay, so if you want to crash your kernel, you can run the cell. Otherwise, I'm going to skip that. And instead, I can import this data into SQLite. And what I will do is show you how I could do it on DataHub, which is to make a new terminal. And then go into DS100, public, go into lecture folder, go into data. Okay, so I have here the data files in the terminal, and I can run SQLite, so SQLite 3. Actually, go back a directory. Okay, so SQLite 3, imdb.database. Okay, I'm going to delete my old database because I have one open, just to show you what it looks like from the beginning. Okay, the files were tab-separated files, so I'll do mode tabs, and then I will run this import line, which essentially says take the data in the titles TSV and import it into the titles relation. Okay, so it'll take a long time. It'll give me a lot of warnings because the data are not formatted super nicely. But for today's demo, I'm going to ignore these warnings, and I believe what SQLite will do is just ignore those rows. So these are, oh my gosh, these are all failing. Okay, that's not good. That's not supposed to happen. Oh, I see. It's probably because I have something open. I was running something on on the computer before. Okay, I have to debug this now. Go into my terminal. And let's hope that it works this time. Let's see. Will that work? Cross my fingers here. Okay, yes, these are the errors that I should be experiencing. So we're going to see these counts go up. I'm going to make that bigger. I believe that these files have, let's see here. If I run this line in Jupyter, I can take a peek at the titles.tsv. So this is what the dataset looks like. Oops. Okay, so the titles dataset has like these columns with like these data. Unfortunately, I have to zoom in to make you guys see in the back. So these lines are wrapped around here, but this is like the first line of the dataset, which says whether it's what the title is, whether it's racy or not, you know, if it was a TV show, like when it was published or when it ended, and how long the movie was. Okay. We also have here the names TSV. So if you look closely here, this is the first line of that data set. We have here the actor Fred Astaire, born in 1899. He was a soundtrack actor and miscellaneous, which is kind of suspicious. But he was known for these particular titles, which you may note are ID columns from the titles data frame. Okay, so we have here a potential joining of these two tables using the titles that the actor or actress was known for. All right, so that imported, we had here like 6 million rows. I have to import the other data frame now, which I believe has 9 million rows. So import that, let that go. And I can see how many rows the data have by running the WC command. The WC command tells me how many lines are in each file, as well as how many characters are in each file. And you'll see here that the names.tsv file has 9 million lines, and the titles.tsv file has 6 million, roughly 6 million lines, a little under 6 million. Okay, so these are some big data sets. All right, that's still going. I have to wait until 9 million. All right, it's getting close. All right, it's done. So if I look at imdb.db, which is the SQLite database that I've just created, you can see that it's about 1.1 gigs, which is about right because each of the individual data sets that went into that bigger data set was about half a gig each. Okay. I can open this database in Python, and I can take the first 10 titles. Let me zoom out a little bit here. Okay. So you can see here that I have the first 10 rows of the titles data frame. And in SQLite, there's a special table called SQLite master, which gives me the schema for all the tables that are in my data set. Okay, so I have here the titles table, and I have here the names table. Okay. I'm going to be using what's called Python f-string substitution. So if I have strings and I want to stick into other strings, the best way to do that in Python is to write f and then put quotes, and then inside of an f string I can do brackets, and within those brackets I can place in Python variables. Okay, so if I do f and then do bracket who, it'll replace that who with the string in the variable who, and a similar thing happens here for the where variable. Okay. What I want to do now is I know that this table is really big, and so what I want to do is slice out some subset of this data so I can work with it in Pandas and try to see some patterns. So for example, what I can do here is look at the genres of my title table and select out only the action movies that have came out, I think, after 1900. Okay, so what I can do is I have here a string, and I put the f in front of the string to say it's an f string. I can write a query here from titles where genres like action. And the way I knew that this had to be action is because I looked up above in my data set and I found that, let me go back here, titles. I found that the genres in a movie are comma delineated. Okay, so I have here, this movie was both a documentary and a short, and those genres were separated by commas. So what I have to do here is use the like operator to say, if action appears anywhere within this genres column, I want to grab that movie. Okay, so I've got that. And what I want to do is add some more restrictions. So let's do year is after 1900. And I don't want it to be an adult movie. And I want, so it has TV shows and movies, but I want only movies. And I think the time should be at least an hour long, but not too long. Okay. And then what I can do is select out the columns that I want. So I can write here, I want this column as the ID column, in a new relation, title column as the title. I can write here, I can take the time column and cast it to an integer. And I can cast the year column as an integer as well, because by default they're written as strings. Okay, I can use this query to create a new table in SQLite. So I can drop the table if it exists. Let's call this the action table, and I can create the table as select action. Okay, so what I've done here is I've made a SQL query called select action, and it's like this long string here. I think if I print it, it'll look nicer. So you can see here that the f string has replaced in the variables with the variables that I want. So the primary title is here, whereas in the original query it was the title variable. I just do this so that it's more readable. So you can kind of see what I'm working with here. And I also use an f string here for the create action table to create one big query, create action table. Okay, so you see here that this is the query that combines these commands here with the create table and the select and all the code that I wrote up above in one big table, in one big string, sorry. Okay. I can run this command, so let's do execute script. And I can print SQL, and I can take the new table that I've created and print out the first 10 rows from that table. Okay, so I see here that I've created a new table in SQLite that only has action movies that came out after 1900 and that are between 1 hour to 3 hours long. Okay. Oftentimes what I want to do is check to see whether the table is small enough to read into pandas. Okay, so I know, so for example in pandas, what I'll do is roughly aim for like 1 million rows. If I have more than 1 million rows, I'm going to have a hard time reading in that table, at least for my computer. You might have a stronger computer than mine. But what I can do to check the number of rows in this new table is select count, put down in quotes, from action. And I can see here that there are only 21,000 rows in this new relation. So that means that I can probably read this whole thing into pandas as a data frame and work with it in pandas instead of in SQL. Okay, so let's read this into a pandas data frame. Pandas has a read SQL method that lets me write in a SQL command and store the result of that command into a data frame. So now I have here a plain old pandas data frame. I can take a look at how many rows and columns it has, and I can start doing some exploratory data analysis. Now that I have the data in a data frame, I can look at the distribution of years. Okay, so it looks like action movies got really popular after 2000. But let's suppose that I want to figure out whether action movies have gotten longer over time. Okay? To figure out whether action movies got longer over time, I can make a scatter plot of the year on the x-axis, the time on the y-axis, and I get this plot. Okay, so what's happening here? So we're getting overplotting, right? So kind of refresh your memory from our visualization lectures from last week. We're getting overplotting because all the points are on top of each other. Why does it look like a box here? Why is it like a hard limit here? Why is this like a hard limit? Why is this also like a bottom line here? Yep. So if you remember from my query, I only kept movies that were between 60 minutes to 180 minutes long. So that's why you have a sharp edge up here. And we don't have movies that came out in the future, although this one looks like it may have come out in 2021 for whatever reason. But most of the movies here are in the past. Okay. So we have overplotting. To deal with overplotting, we can use a kernel density estimator plot. So we can do a year on the time. This will take a while to run because I've got 21,000 points. But what you'll see after this comes out is that, okay, so how do we interpret this? So I would interpret this as, it looks like from the kernel density plot that maybe the average movie length hasn't changed too much, but there's a lot more spread in recent years. We have a lot more really long movies. We can verify this by looking at taking the time column, grouping by the year, taking the mean. So I have here the average lengths of movies for each year in my data set, and I can plot the means. I can show you that the average lengths of movies has roughly gone up over time. Maybe a better way to do this is to do a box plot. So if I add a new column called decade, I'm going to take my year column, floor division by 10, and then multiply by 10 to get the decade. Box plots the decade versus the time. And I'm going to rotate the x-ticks a bit. Okay, so you can see here that I made a box plot of the movie times in each decade, and you can see also from this plot that the average time has more or less increased since the 1930s. And we see here a lot of outliers up on the top because there's a lot more really long movies. Okay, let's talk about some more advanced sampling techniques, more advanced SQL techniques. In SQL, what we can do is also sample rows. So sometimes you might slice out your data, but even that slice is too big. And so one common thing to do in SQL is to take a sample. you can take a simple random sample by taking all the rows in your data set, ordering by a random number, and then drawing the top n number of rows from that data. Okay, so this query here says, put my rows in a random order, and then give me the rows that appear in the top 10 positions. Okay, so that'll give me a simple random sample in SQL. You can actually also do a cluster sample in SQL or more advanced sampling techniques. I'll show you how to do a cluster sample in SQL because it turns out to be pretty useful in real life. Okay, let's do that. So I have here, let's see, a query. I can select star from action, order by random to show you what that looks like, and limit 5. Okay. Like so. So this is a random sample of 5 rows. Again, I can read this into pandas, pd.read_SQL, query, and here's a data frame containing 5 rows. Okay. Let's suppose that I want to take a cluster sample of 3 years instead of 3 movies from my data set. In order to do that, what I can do is actually, okay, how much time do I have here? I think I'm doing pretty good on time. So how about I turn the question to you? How would I select 3 years at random from my original data and then select out all the movies within those 3 years that I've selected from my original data? Okay, so what you should do is figure out how to select 3 years at random and then use those years to take a cluster sample of my original data frame. Why don't you think about it and talk it over with your neighbor for a few minutes? Go ahead. Okay, so I heard some ideas, overheard some ideas. So I ask you this question because it's a very good exam type question. So I can very easily ask you, take a cluster sample of 3 years, or do a cluster sample, and then within each cluster do another sampling technique. So stuff like this is like fair game and easy stuff to put on a midterm, just to give you a fair warning. Okay, so how to do a cluster sample of 3 years? The first order of business is to take a random sample of 3 years. To take a random sample of 3 years, I can take the year column from the action table. I can group by the year to get all the unique years, and I can order by random to get the years in a random order, and then I can take the top 3 years. Okay, so let me show you what that looks like. Let me do 3 years here. Okay, so I have here 3 years chosen randomly from my original relation. Okay, and now what I can do is I can take this year, these 3 years, and then join them together with my original data. If I do an inner join on the year column, then I'll drop all the rows from my original data where the years don't match, which means that I'll keep only the movies that were released in these 3 years. Okay, so I can do that. A simpler way of doing this is to say I can select from the action table, and I can keep only the years where the year appears inside of this query right here. Okay, so for example, I could write where year in, and I can say something like 2017. I think it's a number, so 2018, 2019, like so. And this is not a random sample, but I'll just show you what. Dang it! Thank you. So I have here only these 3 years, and instead of taking hard coding in these 3 years here, I can replace this with this query. Okay, so here I have a cluster sample of 1970, 1987, and 2009. Okay, I can also find out how many years are within each cluster by selecting the year and the count within each group from the cluster sample group by the year column. Okay, so I see here that I've chosen these 3 years, and I have 73 movies in 1952, 219 movies in 1970, so on and so forth. Okay, now this part right here is a bit of syntax that I haven't talked about yet. What I'm doing here is I'm saying, so I'm going to print out this variable to show you what the full completed query looks like. In SQL, you can write subqueries, okay? And you can place a subquery within a where clause. And if the subquery appears within a where clause, then SQL will assume that this query returns a relation with a single column, the year column. Okay, so this query right here returns a relation with one column, and what SQL will do is if I do where year is inside of this subquery, it will run this subquery, get back the list of years, and then use that list of years as though I had hard-coded in the years myself. Okay. Cool stuff. What else I got for you guys? I have a few more things. All right. Let's see here. I'm doing pretty good on time, I think. So I have here the actors and actresses. And I have here a column that says what titles they were known for. Okay. So I can see that, let's see, Lauren Bacall, who I'm not familiar with, was known for these titles here. And what IMDb does is it places up to 5 movies within that column, and it'll put the most famous movie first, followed by the next most famous movie, so on and so forth. Okay. So I have here. Let's look for. Let's say like Tom Cruise. Let me make this a bigger string. Okay, do that. Okay, and I usually place every SQL like subcommand on a separate line just so it's easier to read. That's just my personal preference. Let's look for Cruise. A lot of cruises. So we have a Christopher Cruise, but here's Tom Cruise, it looks like. Anyone have guesses for what these movies are? Top Gun, Mission Impossible, yeah. So we could find out. The way we could find out is we could join this table with the movies table, right? Okay, so let's see here. I have here, do we have time to go over this? Yes, let's go over this. All right, so why don't you take a good long stare at this SQL query, see if you can figure out what it does, and then make sure you and your neighbor agree on what this query is doing. Go ahead. There is some syntax here that I haven't introduced yet. Just take a guess. Take your best guess as to what it does. All right, so how would I break this down if I saw a big query like this and I was confused as to what it was doing? The first thing you can do is look for the from statement. So I look down here and I see that all of this is part of the select. So I'm going to skip this for now and go down to the from. And I say, okay, I'm doing some query on the table containing all the actor names. And I look next at the where. And I see, okay, it looks like I have here where the profession contains the word act somewhere in there, and the person is born after 1800. Okay, and then I can take a look at this select statement, and I see here, okay, well, this one here is pretty straightforward. I'm grabbing out the name. This one is relatively straightforward. I'm taking the year that they were born and making it an integer. This one is not so straightforward. But the hint to you was that if you remembered back here at this table, the movie that they were known for is a long string that contains multiple movie IDs separated by commas. And so my tip off to you here is that this bit of code here grabs out the first movie ID from that list of movie IDs. Okay, so this little bit of substring manipulation here is essentially saying grab the string from the first index or the first position until you get to a comma. And that's what this bit of code here is doing. Okay. This bit of code here says mark whether each person was an actor or an actress. Why do I need the percent signs here? Why can't I just use equals? So I heard it's a string. That's actually not true. I could still do equals on strings. So I'm using kind of like the mini regex or the wildcard character, but why do I need to do it instead of just using equals actor? Yeah, right?
Every single name, or every single row in the table has more than one profession.
Yep. So I see here that this person was an actor, but also a producer and a soundtrack, apparently. Probably a soundtrack maker. So because there are multiple things in here, I need to use the wildcard character to make sure I match all of those. Okay, so this table right here essentially makes a cleaned up version of the actors relation. And what I can do is let's see here, take the actors from, select actors. I can join the actors to the to the action movies table that I had from before, where the movie ID is equal to the ID of the movie. Okay, and I don't want all the columns here. I actually just want the name, profession, the year that they were born, the title that they were known for, and the year that the movie came out. Okay. So I see here that what I've done is I've done the join, I've done the inner join. So I have here every actor or actress with the movie that they're most famous for, as well as the year that the movie came out and the year that they were born. Okay. Let's look at some Avengers. So let's find out the actors that were in the Avengers. I can do from action people where the title of the movie was like the Avengers. Do that. Okay, and I can read in this data frame here, SQL Avengers. We see here Robert Downey Jr., Iron Man. We see here Grace Jones, Julian Bleach. We have multiple Avengers movies, so they all appear in this table here. Anyone know who Mike Capuano is? I actually don't know either, but I think he's like the uncle of, crap. I forgot the name of this person. The person who plays Captain America. What's his name? Sorry? I forget, but he's the uncle of him, and I think he got a cameo because his nephew is like Captain America, so he appeared in Infinity War at some point. I didn't even know. Okay, but he's a congressman, actually, or former congressman. Okay, now, let's see. Skip this cell here. What I want to do is show you, I have here the actors and actresses, and I have here the years that they were born, as well as the years that they were most famous, let's say, like the most famous movie came out. And what I can do is I can compare, using this data frame now, how old the actors and actresses were when they became famous, or when they had their most famous movie. Okay, so because I have this in a data frame, I can do some analysis on it in Pandas and plot the results. And this is the result I get out. How do you interpret this? So I would interpret this as, it looks like male actors generally become famous older in their lives than actresses, for example. That's one possible interpretation. Another interpretation is that Hollywood likes older males more than older females. That's also a fair interpretation. Okay, let's go over what I just covered. So, I had here a case expression in the middle of that long query for actors. Case expressions are essentially longer if-else statements. They're just convenient to know. I have showed you what a subquery is. So I can include a SQL query within another SQL query. Okay, so I can have queries within queries. I can put a subquery in the from clause of a statement. If I put a subquery in the from clause, then what happens is instead of naming a table, so instead of taking the names table or the actors table, I will select out rows from the table created in the from clause. Okay. In a where, what's happening here? Wow, okay. In a where clause, as I mentioned before, there are some special restrictions on the table that you can put in the subquery. That table in the where clause needs to be a single column. So the from clause does not require you to have a single column subquery table, whereas the where clause does if you're using like t.month in something else. Okay. But these two subqueries are very convenient to know because you can do more subqueries within these subqueries to gradually compose up like a really complicated query. So for example, instead of writing months in this select statement, I can write another subquery and do some crazy manipulation that way. Okay, so SQL is a programming language designed for data queries. SQL databases allow us to work with large databases. We can do some complicated and interesting things in SQL, like sampling and composing subqueries using composing complex queries using subqueries. All right, I'll see you tomorrow.